So are there any aspects of this process that you would still like to have explained?
No, that covered it apparently.
Okay.
All right. Some of the other questions. Oh, where did they go? We've got a few coming in here. Hold on a second here. From the October 2009 exam, question number 6.
First thing to do is to draw a bit of a diagram to illustrate what all this information is telling us. And the first thing is that we have a drift, which is the horizontal tunneling that is 3 meters high. And it's the part that's going horizontally. The center of it we can take as being 400 meters below the surface, and the connection from the surface down to that is a vertical shaft that is 4 meters in diameter. And the drift comes out to the shaft and doesn't continue on to the other side. The shaft continues below that 400 meters, another 100 meters, so that the sump or the bottom of it is at 500, and that's where the weight would be for the plumb line. We have going along the drift, along one wall of the drift, a traverse with stations every 200 meters, with a total of a progression of 2 kilometers from the shaft, roughly in an east-west direction to the other end, to point 10. And it's done at 63 degrees north. So the first thing is, how do we take orientation from the surface and bring it down into this drift, into this horizontal tunnel affair? Well, at 400 meters and with the sump, the likely approach would be to use a pair of plumb lines and try to have them as far apart as possible. And we usually say if it's a particular diameter of shaft, then we would go within a certain amount within it. And so, if we then talk about putting plumb lines down, we have to figure out what sort of weight would go on, because we use the value for the weight later on when we're doing some of the uncertainty calculations. And usually the general rule is that you use a weight that is 1/3 of the length, where the length is in meters and the weight is then expressed in kilometers, so long as it doesn't exceed the breaking strength of the wire. If we take the 400 and divide by 3, we have 133 kilograms, which is still within use. And for our purposes, we could say that the weight is just below that 400 meter depth. We don't have to go the full 500 because there's not anything else supposedly below it other than the sump. So we can use the 400 for the calculation for the weight. And that value of P, which would work out to be 133 kilograms, is then used in any of the calculations. The chapter on mining surveying suggests using a 1.6 millimeter diameter wire. If we use the formula for calculating the effective air current, we can get that value, and typically we take that value and divide it by 2 to get the uncertainty as a consequence of the air current coming out. And if we evaluate that with the 3 meter high drift, it works out to be 0.43. We assume that the air is about 1 meter per second in the speed. effect of the spiral shape is a consequence of the storage of the wire, and if we assume a 20 centimeter drum, then with that same wire and the same weight and the typical Young's modulus of elasticity, the spiral shape is a 0.25 of a millimeter, and we take twice of that for an uncertainty, and we add on to that the ability to sense the position of the wire against the scale, which is usually around 0.2 of a millimeter if we follow certain conditions of the amount of swing and taking the averaging and having the scale and estimating to the 1/10 of a millimeter and getting at least a dozen swings either way. So if we then combine that, so that would be 0.43 divided by 2 squared plus 0.25 times 2 squared plus the 0.2 squared, combine them all together and we get an uncertainty of 0.57 of a millimeter for each individual wire. And if we take and have the wires, say, 0.25 in from each side, that means that they're 3.5 meters apart. We have the 0.57 at each one, square the 0.57, double it, divided by, square root it, and then divide by the 3.5 meters. We get an uncertainty in the azimuth being transferred down between the two wires from the surface down the 400 meters to the drift of about plus or minus 47 arc seconds. So basically, if the question doesn't give you particulars about the wire, you would assume the particulars that are typically given in that chapter when you want to give some idea of how well it's going to be done. So 2 plumb lines, determining the orientation of the anchors at the surface, measuring to the 2 wires down below, probably with a Weisbach triangle where the wires are situated so they're very close together and we can look at them almost simultaneously going down the drift. And then we would have to think about what sort of uncertainty would be in that, but that wouldn't be maybe as much of an issue for this particular question. If we consider the rest of it, we have a traverse of points that are every 200 meters. They are, if they're monumented by points on the wall, then we have centering down to about 0.1 of a millimeter. If we choose a particular instrument and a certain number of sets, we can predict how well the included angle would be measured at each station, and you accumulate that over the length of the traverse. The concern, of course, would be with that style of traversing that there is the systematic effect of refraction. We don't have any information on what the temperature gradient might be, but there are some suggestions in the chapter as to what typical magnitude there might be. So if we want to talk about procedures, we might want to say that because of the potential effects of lateral refraction, we may want to introduce also some azimuth measurements in order to cut down on that influence, which will also improve the azimuth transfer just with the traversing.